All right. Good morning, everyone, and I hope you can all hear me. Today, we'll be looking at the concept of model for computer sciences, and we'll be looking at automata theory, automators, and grammar. In the previous classes, we looked at a bit of mathematical proofs, uh, premise to conclusion. We looked at the truth operators. Then we moved forward to the concept of language, defining what languages are, the rules governing language, and how language can be made to be meaningful by introducing syntax and also semantics. We looked at formal languages and a host of other things. So today, we'll be delving into the crust of the course, which is on automata theory and computability, right? So, first of all, we understand models to be any form of abstraction to represent some properties, some physical properties of uh, a system. Now, when I mean a system, it could be any kind of system. It could be the computer system. It could be a system of operation. It could be anything system, right? So once we abstract some of the properties out from reality, out from the complexities that exist, then a model is said to have ensued, right? So we're going to be looking at a number of types of model. Then we'll dive into computer models and automata, right? And we look at how some of these automators can be formally defined and how they can be represented using tables and using diagrams. So as a form of introduction, we want to look at the use of models in science and engineering, right? So in most field, designs are based on models. So for you to carry out any form of uh, design, any form of construction, any form of simulation, you must come up with some kind of model. Now, this is because it is often impossible or impractical to test whether a problem solution is adequate by directly applying it to the real world. For instance, if you needed to build a huge building, for instance, a mansion, it will not be nice or it will not be wise for you to just start the construction without pre-plans, without maybe checking where you want to put the doors, the direction of wind for ventilation, uh, the the height of the building, and a host of other things generally, right? So for you to start any form of design, you must have a template that you want to follow to arrive at what you want to achieve. Now, I'm sure some of you are aware of some architects, right? Once once they want to erect buildings, they also draw some form of model to represent the old buildings that they intend to construct, right? And those lines, so-called lines, they will start explaining to you, this where the door is, this where your bed is, this where the window is, this where the wardrobes are going to be, and all that. And you'll be wondering that, oh, what's this fellow saying? But that is an example of a model representing a physical quantity. What the architect has simply done is to abstract some properties of the building into simple details that could be understood by just using those lines. Now, for instance, building a bridge or a house without any previous design decision based on some modeling of the problem will not be a good idea. So the models may be physical, right? Where observations and measures on the real bridge can predict the behavior of the actual bridge to be precise. So a model can be physical, right? But there are some lapses that we observe when you are talking about using physical model. So, however, physical models cannot solve all problems for obvious reasons. Now, what are those reasons? The first one is that it may be uh, difficult or highly expensive to build a physical model of the phenomenon under study. For instance, if you need to build a 27 or 30 story skyscraper without any plan, now I think it will not be so cool to just go building without any plans, or you feel that, okay, by the time you finish building, that's when you now start testing some of the weights, the pillars, the columns, and everything. Now, that can be very disastrous. That can be very dangerous. What about if there's a fault or a fault line along a particular axis of that building? That means you have to demolish the whole building and start all over again. So using a physical model is usually very expensive, right? Especially when you do not have a model to represent some of the properties that you feel is important to that building. So a physical model may be helpful after all major design decisions have been taken as an experimental tool for quality assurance. So physical models could just be a prototype when you have simulated all the different types of decisions you want to take on the building. For instance, an individual may be more than 7 feet tall, right? And the regular door, I feel, should be uh, maybe, I'm not too sure, maybe 6 feet. Now, somebody who is 8 feet tall and you have designed a structure, or maybe you have designed a model that could just accommodate somebody who is 6 feet. So what it means that at any instance of time, when that individual wants to get into his house, he has to bend his neck. And that can be inconveniencing, given that that is where he's going to live for a long period of time, right? So once all decisions, so I think if you now come up with that kind of design for the individual, it tells you, look, I'm quite tall and I don't feel that this dog will take me. So you go back to your design. So you change all the doors to accommodate his peculiarity. Maybe you can just make all the doors to be 10 feet, right? So even at that, at least he could just enter without having to bang his head on any of the doorways, right? So after all those design decisions have been taken, then physical model, which is a prototype, can now be developed. However, during the use of the physical, during the development or building of the physical model, some corrections can still be made, but it is not going to be major corrections that has to be made. So building several different physical model to explore entirely different design will be unacceptable and very expensive. Now, physical models are more supportive of design evaluation rather than design synthesis. So what are design evaluation? Design evaluation, okay, will this work? Will this be okay? Can this carry the weight? Can this do, that means after you have abstracted, you have done your modeling properly, then you now evaluate all those things that you have assumed in your model by maybe some mathematical model or some form of different things, right? So once those things have been done, then physical model can come in. However, other models are used to synthesize some of these ideas. You bring up models, then maybe you draw, just like the example I gave earlier, you draw a particular model, right? And the person is 6 feet tall. No, it's maybe 7 feet tall. Then you come to adjust in such a way that it can now accommodate this tall guy, right? So you now subject those model into actual buildings. So the person comes, he tries to enter the door. Oh, this door is quite tall, so I can enter easily. What about if the people interpreting the model decides to make it 6 feet? Maybe they're already used to the normal size of building. Ah, no, it has to be 6 feet tall. And they say, no, the designer made a mistake. And they decide to make the building doorway 6 feet. So what happens? They can now correct some of those mistakes they have made. So what, in essence, is that physical model are more useful for design evaluation. So it may be difficult to translate the result of experiments performed on models into results holding for real cases. So for instance, if you decide to use physical model and you are trying to, maybe you build a prototype and you are making corrections here and there, here and there. Once you have done with all the corrections, to transfer those corrections into a real building becomes very difficult because there's a likelihood that you did not even take maybe take any notes on what you have been correcting, right? So trying to duplicate it in another building may be another kind. Yeah, so it appears I was thrown out. So I hope you can hear me now. So if you can hear me, just type, okay, thank you. Sorry for that break in transmission. Yeah, can you see my screen now? Yeah, is my screen visible to you? Okay, thank you. So let's continue from where we stopped. So we said that we're about defining a formal model. So a formal model deals with mathematical objects that represent abstraction of the real entity to be modeled. So what mathematical model deals with generally is about abstraction. Now I'm sure you have done some things on abstraction, right? So I feel yeah, things you are used to already. So abstraction is just taking some properties, right, as it concerns the the system that you want to model, the model that you feel is important to you. You take some of the properties, then you represent them using some formal languages or some formal or some kind of formalism, right, to represent the entities you wish to model. So formal models allow the user to apply the rigor of mathematical reasoning in the derivation of properties of the entities being modeled, right? So if you intend to maybe abstract some properties of human life, you could want to look at the movement of human, right? So with your knowledge of physics, you could start with the U plus AT, right? So that is one aspect. You want to model the velocity of an individual who probably was in a starting state of rest or was in a form of a constant velocity, right? And there's a concept of acceleration and time that requires for that acceleration to take place. So if you want to model that aspect of life, that aspect of human existence, then there's a need for you to be knowledgeable in a particular area or formalism as it regards that area of study. Now, I hope you can still hear me. Now, for example, a set of mathematical equations can describe the structure of the bridge, that's the bridge we talked about earlier, and the force applied on it. So instead of talking about the whole construction, right, we could look at just one aspect of it, the force applied on the bridge. Why do we want to simulate or why do we want to abstract that property? It is simply to test the carrying capability of that system in such a way that the system doesn't collapse under heavy weight, right? So if you are simulating the weight a bridge can carry, you are testing it because probably you want articulated vehicles to be able to climb. Maybe you want to see if there's earthquake, can it withstand all those pressures and all that. So after solving such equations, the designer can foresee internal efforts of the bridge to be designed. Going forward, formal model basically requires a few things, right? The first one is formalizing the problem. Now, this is, you translate the real problem into a denotation within some mathematical formalism, right? So that means you should be conversant in the area of that formalism you want to abstract to. Now, you cannot abstract into mathematics if you do not know anything about mathematics. You should not abstract into physics if you do not know anything about physics. So solving the formalized problem, this is done by means of tools provided by the chosen formalism, right? Now, okay, solving the problem. So you do this by means of tools. When I mean tools, that means if you are solving using mathematical, if you have abstracted using mathematical formulas, and you have abstracted into some set of mathematical equation, as a mathematical student, you should, as a math student, you should be able to, in a way, work in some kind of form of a system of equation or linear equation or quadratic equation or any form of equation. So you should be able to solve problems in the area that you have abstracted to. And the next one is interpreting the result obtained from the model. Now, this is done in order to derive or evaluate design decisions. So once you have done a lot of simulation, you have maybe put in, if I put an articulated vehicle carrying another articulated vehicle, can this bridge survive? So what force of cement, what reinforcement do I need? What will be the, so you just test a lot of parameters to be sure that everything you want to use in constructing that bridge has been well simulated. For instance, I'm sure you are aware that the Fourth Mainland Bridge is about being constructed. So a lot of feasibility studies would have been done. A lot of simulations. Now, do we allow tanks, all these trailers to be able to pass on it? As again, the Third Mainland Bridge that is not allowed. What are the properties? What is it going to be towed? A lot of things would have been done. Then once all those simulation has been done, then we'll now interpret the result from the model, right? So this is done in order to derive or evaluate design decision. So after doing that, you can now decide, okay, these are the decisions I want to take. Trailers can now pass the Fourth Mainland Bridge, right? Then it will be so high in such a way that ship or maybe boats can drive under the bridge to take people from maybe island to mainland, vice versa. Maybe you could, when that is in place, then we could now break up the Third Mainland Bridge by Yaba, by Unilag Lagoon Front. So we can now construct an underpass. Instead of going round and round, we could just bypass all traffic and just enter Unilag from the waterfront. So those are decisions that you can take. Now, several errors can occur during this process too, both during the informal steps 1 and 3, and during competition in step 2. Thus, design of complex engineering projects often requires a careful use of several models of different types. So that means we have different models for different purposes and of different types. So model plays an essential role also in every branch of science. The fundamental emphasis of modeling in science is more oriented towards interpretation of reality, whereas in engineering, it is more oriented towards design. So if you are abstracting in the field of science, which computer science is one of it, it is more supportive of interpretation of reality. Now, reality in itself is too complex for us to be able to represent it just once with a blue of model. So we have to use different types of model to represent different aspects of reality. So by abstracting, it makes our work much easier. So in engineering, it is used more for design purposes, especially construction of bridges, houses, and a host of other civil engineering work. So a model in science embodies our understanding of certain phenomena. As such, it abstracts away from many fine details. So that is about what abstraction is. It doesn't bother you with all the details there is, right? It only reflects certain macroscopic properties of their aggregated behavior. Now, I think some of you are aware that once we want to draw the representation of human, now I'm sure you can see my cursor moving. You can draw something like this, right? This, we call it torso, but in those days, we call it skeleton 101. Now, this has represented the human being, a human. with all the complexity that is happening in human, once you see this torso, you know that this is representing a human, right? So what aspects of the human of this human torso do you want to further abstract? So this is a form of abstraction, and this is a form of model. A model representing the human, as it were. So as such, it abstracts away from many fine details and reflects on certain macroscopic properties of the aggregate behavior. Now, it is exactly through abstraction that our models allows us to master the enormous complexity of real life phenomena. So in a way, you cannot model all the complexity in life. You only abstract some properties, right? And after abstracting those properties, you can now make use of them for whatever you need them to do. So a model is adequate if the result obtained by experimenting or reasoning on the model reflects observable properties of the phenomenon under study with acceptable approximation limits. For instance, look at this torso that I've drawn. Now, it has represented the human head. Now, of course, you know that in the human head, you have the eye, the nose, the ear, the everything. Then this is the neck. Then you have the hand has a finger, the elbow, everything. Then you have the trunk, which has the stomach, the intestine, everything. Then the legs. So this, in its way, in its simple as it is, has represented sufficiently the structure of the human body, right? So if you now look at, he said a model is adequate if the result obtained by experimenting or reasoning on the model reflects observable properties of the phenomenon under study. So when you look at this torso, it has reflected observable properties under study. What are we studying? Human, right? So this, in a way, has sufficiently represented what can be found in the human body within acceptable approximation limits. So everything we have done here, we have put one big circle to represent all the functionality in the head. This longer one line is representing the hand, the trunk representing the body, then the legs. So within approximate limits. So we can say that within approximate limits, this torso has represented the human form. In other words, the abstraction embodied by the model captures exactly all properties of the phenomenon, which embodies certain abstraction. Okay. Moving forward, let's take an example of abstraction. Now, we said in a yard, there are both chickens and rabbits, right? The total number is 20. Furthermore, the total number of legs is 60. How many chickens and rabbits are in the yard? So what are the suggestions that you have? Yeah, if you have any suggestion, you could raise up your hand, so we'll call you. Suggestions? Any suggestion to modeling these issues that we have raised? Nobody? Or do I call anybody at random? Huh? Are you listening at all? Can you still hear me? Hello? Can you still hear me? Okay, you can. So why are you not responding to my question? How can we abstract this problem? All right. Let's continue. So a background knowledge of equations will probably be required for you to do anything here. And the thinking may be in the following ways. So the first thing is that you represent each of the quantities mentioned in the question with some kind of alphabet or a form of symbol as you have chosen. So we say let X and Y be the number of chickens and rabbit respectively. So we have X to be chicken and Y to be rabbits. The question further told us that there exist animals with 2 legs and those with 4 legs. It went further to tell us that total animal is 20 and the total legs is 60. Now, with your knowledge of agric science and also by maybe observation, you know that once you are talking about legs, you know that chicken has 2 legs, and which other animal? Rabbit has 4 legs. And remember, you have represented your rabbits with Y and your chicken with X. It further told you that the total number of legs equals 60. So when you look at equation 2, you have 2x plus 4y to be equal to 60, telling us this is representing what? The formalism of legs, or the abstraction of total number of legs. Then here is abstracting the total number of animals, saying that the total number of animals is 20. So that means when you add x plus y, you add chicken and rabbits, it gives you a total number 20. So this is a form of model, and we have abstracted the long question that we have here, like here. We have abstracted it into just 2 lines of system of equation. Now, this is where we're talking about earlier, that if you do not have any knowledge in systems of equation, you may not be able to abstract one. Not only that, even if you abstract, you may not be able to simulate properly in that domain. So there is a need for you to understand formalism, the area that you're abstracting to, and the tools for solving issues in maybe formalism. So once you solve this system of equation, what do you think your answers will be? Has anybody solved that problem already? Now, by the time you look at the first one, when you make y the subject of the formula, so you have 20 minus x equals y. So when you substitute for y in equation 2, you should be able to get the values that y are. So when you solve those systems of equation, okay, x and y equals 10 respectively. Okay, thank you, Kazim, Stephen, and Peace, and Akinola Isaac. So you can see that you must first of all understand the area that you are working in, that's the formalism. Then you should be able to use the tools in that area to solve or to simulate in that direction. So the solution to the equation yield x equals to 10 and y equals to 10. Thus, in the yard, we have 10 chickens, or is there chickens or chicken, and 10 rabbits. Solving this equation would be much difficult for a student who is not familiar with equations or systems of equation. The reason for this difficulty is essentially in the inability to abstract away from the actual problem. That is translating it into a suitable formal notation. That is the equation that also provides some mechanical tools for its solution. Another example is this. You have suppose a ripe apple falls from the top of an H-meter high tree. We wish to evaluate the time t required by the apple to reach the earth, right? So we want to look at the time. Right? and want to be in relation with the height in meter, right? And what again? Of course, now there are a lot of silent notations here. So we say, suppose a ripe apple falls from the top of an age tree, we wish to evaluate the time t required for the apple to reach the earth. Now, if an individual who has not done anything in physics, right, attempts to solve this question, it becomes a lot of problem for the individual, because you just have h and t. What about gravity working on the apple as it drops from the height of the tree down to the earth? What was the state of the apple before the descent? So, of course, we know that the apple has a resting state at that height h, right? And gravity will work on it to be able to descend downwards. And there's a time from 0 to the ground that before striking the ground. So, well, I think this for a form of comic, really, that some students just resumed from master strike, and one was asking the other one that was it in 400 level or 300 level, that you should remind me. So the other one said the worst is that I don't even remember the course I was studying. So that's serious. So let's hope that we do not have any other strike. Moving forward, from physics, a simple abstraction under material particle is needed. The only applied force is its weight. According to Newton's gravity law, the apple has an acceleration of 9.8 meters per second squared. So the relation is, we want to calculate the height with respect to t. So we have u plus half gt squared. Since the starting velocity of the apple is 0, that's u to be equal to 0. So the only relation we have, that h equals half gt squared, right? So with this, we could calculate the time if we are given the height, and we'll just find the square root after making t squared, t the subject of the formula. Hence, in knowledge of the formalism and abstraction should be familiar terrain. You see this? The knowledge of formalism, right, and abstraction should be a familiar terrain for students of modeling. Yeah, do you understand what I've taught so far? Have any response? Do you have questions? Do you understand what I've said so far? Waiting for your response. Okay, Uday Thomas, so it is clear, sir. All right, do you have any other response? You have questions? Is it clear enough? Do you understand what I've taught so far? Response? Well, do I assume that you all understand what I've taught so far? Do you understand what I've explained so far? Yes, Kazim, you said, I suppose to be able to abstract, the student must have the prerequisite knowledge of relating matters. Well, that's also, it's just true. That's correct. Not only relating matters, but where to abstract to. That's correct. Is that a question or a suggestion or? Okay. All right. So moving on, I feel some of you are in some other. I was saying what I learned. Oh, okay. Thank you. I don't know, maybe some of you are in some other places or you are not in class. You just want to make attendance and run away. Okay. So moving on, finite state automata basics and theory. So in theory of computation, the theory of computation begins with a question that, so what's a computer? So you may feel that's a silly question because you know what I'm teaching you on is a computer. However, it goes beyond that. But these real computers are quite complicated, right? That their whole working system is too complicated, too much so to allow us to step up a manageable mathematical theory of them directly. So what do? We take some aspects that is of importance to us. Then we abstract that aspect into some form of formal model. Then we carry out some form of simulation on them, right? So instead, we use an idealized computer called a computer model. As I said in the opening of the class, that what we'll do generally is to have some aspect of computing, especially when it has to do with the developmental aspect of computing. That's what we'll be modeling using automata. So different automaton will be developed to simulate certain aspects of the computer system and its evolution. So as with any computer, any model in science, a computational model may be accurate in some ways, but perhaps not in other ways. Thus, we will use several different computational models depending on the feature we want to focus on. So for some models that we have the finite state machine, right? We have the transducer and the translators. We have the push down automata. We have the Turing machine and a host of others, depending on what aspect of computing we want to focus on. So we begin with the simplest model called the finite state machine or the finite automaton. So automata is the plural and automaton is the singular. So one finite state machine is called finite automaton and several of it is called finite automaton. That's one of its automaton, several automata. So finite state automata. So what's the finite state automata? Finite state automata are good models. So we have established that finite state automata is a model for computers. And the aspect that we want to concern ourselves with is that it has extremely limited amount of memory. So we want to look at the memory aspect of the computer itself. So that's the aspect we want to look at. So in fact, we interact with such computer, so what can a computer do with such a small memory? Of course, it can do many meaningful things, right? That, they are present in all our day-to-day life, where in fact, we interact with them daily. You interact with it, you have interacted with them today on different fronts. So in fact, we interact with such computers all the time as they lie at the heart of various electromechanical devices. Now, Yes, sorry. I think I was thrown out briefly again. Yes, I hope you can still hear me. Can, can you hear me, please? Oh, okay. Thank you, Kazim. All right, thank you. Olukolatimi and Ani Mashaun Tobiloba. Ude Thomas. All right, thank you all. So, where was I? Okay, so I said you interact with all this, almost every. I think I was giving an example of DLI. And once you get to the DLI, there is the front door before you get to the admin. Once you step on the footmat, the door opens for you to just walk in. So the description is that an automatic door has a pad in front to detect the presence of a person about to walk through the door. Another pad is located to the rear of the door so that the controller can hold the door open long enough for the person to pass all the way through. Also, so the door does not strike somebody standing behind it as it opens. So this configuration is shown in the next slide. So you have that this is where you have the front panel here. So this is the door. So you see, maybe you see one fellow. No, sorry, clear. So you see one fellow walking towards the door in the front, right? So what happens that as soon as you step, there's a sensor here that makes the door open up, right? For you to walk through the door. However, if somebody is inside and he is also on this pad, the door remains open until the two of you move forth and back, and it remains closed. It remains open so that it doesn't injure anybody during the process, right? So the controller is in either of two states. Is either in open states or closed states, right? Representing the corresponding condition of the door. So as shown in the following figures, there are 4 possible input conditions. So when we talk about input, what can cause a change? What can cause a trigger? So those are inputs. Now we have 4. The first one is that somebody is standing on the front panel. Another one is that somebody is standing on the rear panel. There, it could be that 2 people are standing simultaneously at the front or at the back, or you do not have anybody on the system at all, on the door at all. So these are the 4 possible input conditions that you could have. Now, this is a state diagram showing us what the automatic door, what happens in the automatic door. So you see here, you have front, rear, both. These are the inputs for it to remain open. So if somebody is in the front, somebody is at the rear, or people are on both sides, the door should remain open. So it's a transition. Okay. So this is a transition, right? Telling us that remain here. So if the door is at a closed state and it received somebody on the front panel, what happened? It moved to the open state. However, if the door is closed and somebody is at the rear, somebody is maybe 2 people are in front or at the back, or nobody is here, it should remain closed. That's what this says. However, if you are in open state and nothing is in front and nothing is at the back, so what happens is that close the door so that you don't allow the gas of the AC to run away. So moving forward, we have what we call the state transition table. for that diagram that we have seen here, for this diagram. So here you have the states. We have two states. The states are those in the circle, right? This close and this open. So we have the state to be closed and open. Then we have the input combination, the likely input, neither, front, rear, and both. So these are the possible transition that can happen during the transition process. So the controller moves from state to state depending on the input. So upon when the controller gets a particular input from a set of input, it moves from one state to another. So what it means that an automaton is a self-propelling model that upon the receipt of an input, it triggers a movement from one state, let's say this is state A, to another state B. So upon the receipt of an input, it moves from the state A to another state. So states are represented with circle, right? And there's an arrow, a directional arrow showing where the so this, let's assume it takes one. This is the input, this is state A, right? And this is state B. So you are state A and you receive an input. So this one is an input. You move to state B, right? So when in the closed state and receiving input neither or rear, it remains in the closed state. So still referring to the automatic door. In addition, if the input bolt is received, it stays closed. That is, it is closed. It stays closed because opening the door risks knocking somebody over on the rear part. But if the input front arrives, it moves to the open state. That means if somebody stays on the front part, right? So what it does is that it opens the door for that individual to enter. Now, in the open state, if input front, rear, or both is received, it remains open so that all of them can quickly run inside or outside. So if neither is received at the open state, it returns to the closed state as it was before the whole process started, right? So moving forward. So for example, a controller starts in a closed state. So oftentimes we have what we call the states that will meet the controller. For instance, if you get to E304 in the morning, there's a likelihood that if you are the first person, all the ACs will be off and all the fans will be off and the light will also be off. So that is the state, the initial state that you have met the lecture theater. And it's usually represented with an arrow pointing at that state. So if I ask you to describe the states that you met E303 or E304 at any instance of time when you enter, you observe what state was that lecture of. So probably you made the light off, AC off, fan off. That is the initial state. So the next thing you do is that you move from the initial state to another state. And what is the state? Probably you on the lights, you on the fan, and you on the AC if you are the first person. So you have altered what was in the initial state A of the lecture to another state B, where AC is working, the lights are on, and the fan is also rolling, right? So these are the terms that we use when defining states in the automata of an automaton. So, for example, okay, a controller might start in a state and receive the series of inputs. So it receives series of inputs. These are the series of inputs. So it now makes, so these are a series of input that this will take. It then goes through this series of states, close, which is the starting one, open, open, close, open, like that. A controller is a computer that has just a single bit of memory. So what are we abstracting here? We're abstracting the memory of a computer. Just to remember, okay, I'm in state open, I'm in state close. Capable of recording which of the two states the controller is in. Other common devices have controllers with somewhat large memories. For instance, in an elevator, if you go to a Senate building, controllers, okay, in an elevator controller, a state may represent the floor. The elevator is on, and inputs might be the signal received from the button. So oftentimes we define the internal working of the system or of the computer we want you to model. Moving on. So this computer might need several bits to keep track of this information. Controllers for various household appliances such as dishwashers and electric thermostats, as well as part of digital watches and calculators, are additional examples of computers with limited memories, right? So the design of such devices required keeping the methodology and terminology of finite state automator in mind. So we know all this now of the description of an automaton. So there should be a way we should formally describe this automaton so that all ambiguities about that system can be trashed. For instance, if you want to describe the elevator, you can describe the working of an elevator in different ways. I can tell you that the elevator will be on the 12th floor of the Senate building as the initial state. I can tell you it will be at the ground floor at the initial state, right? So it depends on the wording of the automaton that will now determine how you model that automaton, right? And how you define it formally. So how do we define all this formally? So finite automata and their probabilistic counterparts, Markov chain, are useful tools when we are attempting to recognize patterns in data. Those devices are used in speech processing and in optical character recognition. So Markov chains have been used to model and predict price changes in financial markets most of the time. Now, I'm sure some of you who are dealing with Bitcoin would have probably looked at the Markov chain to predict when the Bitcoin should have crashed. But some of you were still having hope beyond hope. And unfortunately, some of you lost a lot of money. We'll now take a closer look at the finite automaton from a mathematical perspective. We'll develop a precise definition for it of a finite state automaton terminology for describing and manipulating finite state automata and theoretical result that describes the power and the limitation. So I think Dr. Sanaiki will be taking you on power relation and a comparison of the power relation of each of these automaton. Which one is useful for which one is more powerful in what area, and it goes on. So this is a summary of what we'll be doing in automata theory. So we'll develop precise definition of each of the model that we want to come up with. We tell you about the terminologies for describing that model and how the internal manipulation, the transition function, right, and the theoretical results that describes the power and the relationship that exists between all these representation that we have developed. So besides giving a clearer understanding of what finite automata are and what they can and cannot do. This theoretical development will allow you to practice and become more comfortable with mathematical definition of any model that will come your way, the theorems and proofs in a relatively simple setting. So I hope as we start properly now, you will understand the concepts that we're driving at. So this is a diagram called a state diagram of a finite state machine called M1. So we want to say that this machine is called M1. All right. Would you, in the next 5 minutes, drop in your matric, your name, your matric number? So we have 5 minutes to do that. Your name and your matric number. So I have 71 people, so I'm expecting 70 names. That's I am one of you. I'm one of those people online. So we want, okay, I think it's now 72. So we need only 71 names now. So once it's, if I have more than 71 names, that means all of you are absent. And if you write your name and you exit, at some point, I will take another attendance to compare. So that means you just have half of the attendance. So we have 73. So we're expecting 72. Somebody is just going out and coming in at his own time. Okay. So we need 20 more names. Now somebody is just joining again, making 74. Don't worry. I'll put all of you in waiting room now, so you're not going to join. If you are just joining, just don't bother putting your matric number, because I can't be in class and some of you are just joining. So please put in your matric number. We have 59 names already. Please be fast, just have 5 minutes. After 5 minutes, I get out the attendance, and that will be the end of attendance writing. Now I'm seeing some of you just joining anyway, so I'm going to pull out your name from the attendance. We have 9 more names. We have 5 more names. Yeah, I'm waiting for those 5 before I continue. 4 more. 2 more. 1 more name. All right, so I feel that I have all the matric numbers registered already. So if you just join the class, don't bother putting your name, because I'm seeing as you are getting in and out. I'd say you should not put your name. One name has entered. I'm going to flush you out. All right, going forward. So this is an example of an automaton, right? So you see that we said initially that we have an initial state as a state that you met the automaton, and we have an arrow pointing from nowhere to that state. So this is the arrow. So any state that an arrow is pointing to from nowhere shows that that is the start state or the beginning state, right? So this is an example of and automaton. Moving forward. So the figure above is called a state diagram of MI. So that diagram was named MI. Now it has three states labeled Q1, Q2, and Q3. Now look at this these are the states. This is state Q1, this is state Q2, and this is state Q3. That means this MI has how many states? Has three states, which are those circles: 1, right, 2, and 3. So we have established that MI has three distinct states. Now, looking at it again, you observe that the start state Q1 is indicated by the arrow pointing at it from nowhere. As I've said earlier, this is an arrow pointing at it from nowhere, telling us that this is an initial, an initial state. That means the beginning state. Moving on, you will also notice that the initial state is indicated by Q1. See, this is Q1. This is the arrow pointing at it from nowhere. So the accept states. Now, if you notice one of the circles, one of the states has double circle, right? Is the one with double circle, and it's called the accept state or the final state. Look at Q2. You can see it has double circle, right? So this is the accept state. It has double circle. So for anything we try on this, all the trying, all the movement must end here. So if the inputs combination ends here, we say that that input or that string or that language is accepted by this automaton. Else, we say it is rejected. So the arrow going from one state to another is called transition. So you see all these arrows, all this one, this one, this one, this, and this. They are all called what? The transition. So sorry, I need to get the attendance out. So I'm going to stop sharing for a bit. It's recorded, I don't think so. Bad network just took me out on this. I need to copy the attendance and get it out. So please let me stop share for a few minutes and I'll come back. So I'm trying to get the attendance out quickly. So once that is achieved, I will continue with the class. Oh, all right, so I've got the attendance out. Yes. Right, so let me share, continue. Yeah. Yeah. Okay, so I hope you can see my slide now. Yeah, can you see my slides? Are you still in class at all? Okay. All right, thank you. All right, so let's continue. So I was saying that these are the transition, all these arrows. Now you see they are directional arrows. They have directions on them showing us where the direction is. So these arrows are quite important. It's not just lines. They are lines with arrows telling us the direction they are pointing. So we know where to go per time. All right, so moving on. What again can we look at here? So the arrows going from one state to the other are called transition. So when this automaton receives an input, such as this string, it processes that string and produces an output. The output is either accepted or rejected. So how do we process this input? So the input string we want to look at is this 1101. So for example, when we feed the input string 1101 to the machine M1 in the figure, the processing starts as follows. Okay, so let me move this diagram here so it can be easy for us to see. Okay, now can you see the diagram, please? Can you see this diagram that I've moved here from the previous? No response. Oh, all right, you can see it. So now let's run through what this is about. So what are we trying to run it through? We want to run this input string. So let me copy this input string and keep it here. So that's the input string we want to move in. So here, now this telling us that the start point is at Q1. So you see this arrow is telling us that that is where we need to start our input taking in from. And we take the input from what? From left to right. So the first one we take is this one. The second one is this one. The third one is the 0. And the fourth one is this one. So let's drive them in and see. So at Q1, you take an input from this. So what you are driving is what? 1, 1, 0, 1. So it says you take in 1. So once you're at Q1 and you pick up a 1, it moves you to where? Q2. You can see this label 1. Let me explain again. You are at, this is 1, 0, no, you have 1, 1, 0, 1. That's the input string we want to pass through this automaton. So here it says that we're at the starting point Q1. How do we recognize the starting point? Where the arrow points to from nowhere. Then knows that this is where we are supposed to start any form of calculation from. Whatever is happening behind this place, we don't care. So the first one is that we take this input 1. The input 1, when you're at Q1, you take in this input 1, and you can see this label 1. It takes you to where? Q2. So you read 1, follow the transition from Q1 to Q2. So 1 takes you to what? Q2. The next one you read, now you are now at what? Q2. Once you're at Q2, you receive a 1. You read a 1. It takes you where? Still remains at Q1. So you read 1, follow the transition from Q2 to Q2. So you're at Q2, you read this 1, you see this arrow telling you that you should stay, sorry, you see this arrow telling you to stay at Q2, right? So still 1, 1, 0, 1. So 1. So we have processed this, and we have processed those who have just processed this 2. So the next thing is that you are still at Q2, haven't taken 2 inputs. The next one you are supposed to read is what? 0. So this 0 takes you where? This is 0. This direction is taking you from Q2 to Q3. So you said read 0 follows transition from Q2 to Q3. So it takes you to Q3 upon reading 0. So you are done with this. The next one you are supposed to take is a 1. So you see here, either you take a 1, a 0, or a 1. It takes you back to Q2. So read 1, follow transition to Q2. So what you notice that having exhausted all the symbols in this string, the automaton arrived at what? Q2. And Q2 is what? The final state. Just as we looked, I'm coming. Let me clear up. Just as we defined here, we said when the automaton receives an input string such as this, it processes that string and produces an output. The output is either accepted or rejected. So how do we determine if it is accepted? It is accepted because M1 is at an accept state. What is an accept state? An accept state is this place that has this double circle, which is Q2. State Q2 at the end of the input string this. At the end of this input string, we're able to arrive at what? Q2. Now let's assume that when you were here, you could only remain at Q3 when you are finished reading the input string. That means that this is not the accept state or the final state. Hence, this automaton has not accepted those string or is not part of the language that can be accepted by that string. So look at this figure again. Can you quickly test this language or this string if it's going to be accepted by this automaton? Yeah, get a sheet of paper and quickly do it, and let's have your answer. Is it accepted or is it rejected? Quick, you have 2 minutes to do that. I want your response. Is that accepted or rejected? Can you see hear me, please? Please test the automaton with the figure. So test the automaton in the figure with this and conclude. So you tell us if it's accepted or is rejected. Okay, there's a response here. Accepted. Oh, thank you. Who is this first person? Sorry. Let's see. Okay. So Julius Ali Brown. Thank you. Ademola Oriano. Thank you. Okay, accepted. Okay. Well, I hope those of you typing accepted, you understand how it was done. So if you understand how it was done, please, Q2 is accepted. I didn't say you should test Q2 now. Ayodele, I say you should test if that string is accepted. So if you do not understand how that was tested, can you just tell us no? Can you just type no? If you don't understand that was done, just type no so that we'll run it over again. If you don't understand what they have done to arrive at it being accepted, just say type no. Okay, Ajay Puja. Okay, Momini Abdullah. Okay. Wait again. So we have two people who do not understand. So let's quickly run through it and see why it wasn't accepted. So we want to test this string, right? To see if this automaton will accept it. Now, you understand that, let me put on my notation. You understand that this is the initial state, right? This Q1 is the initial state. So when you are the initial state, you first of all pick the first symbol, which is 0, on this string. You look at it, you're at Q1, you read 0. So this is reading 0. You still stay at what? Q1. The next one is that you read A1. A1. This one will take you to where? Q2. The next one, you read a 0, right? This is reading 0 at Q2. It takes you here, right? So the next one, you read a 1. So 1 will take you back here. The next one, you read a 0. 0 brings you back to Q3. The next one, you read another 1. 1 will take you back, because you can either read a 0 or a 1. It takes you back here to Q2. Then you read a 0. 0 takes you back. So you are just looping. You read a 1. 1 brings you back here to Q2. You read a 0. A 0 takes you where? To Q3. And you read the last 1. 1 takes you to Q2. So by the time you read all this, you just be looping here up until the last one, which is 1, which will take you back to the accept state. So once the whole input evaluation brings you back to Q2, it means that the string is accepted, right? So what else? Let me see. Ajay Nifuja, do you get what I've just explained now? If you don't, just be open. I will still explain if you don't understand that. Do you understand the logic that I've just explained? Samad. Oh, thank you. So Mumi Abdullah, I understand. Adini Fuja, do you understand now? No. Okay, let's look at it again. Now, let me use another pen so that now, just be typing so that I'll be seeing your response. Okay, Kazim, Lawrence, you don't understand. Okay. So let's look at it again. You understand why we call this. Oh, this one is not clear. Let me use better. Okay, you understand why we say this is the initial state, right? Just be typing yes or no so that I will know where you got lost. Okay, good. So you are, let me move the response so that will be seeing your response. So you are here at the initial state. This is a set of inputs we want you to test 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. That's what we want you to test. So this is where you are Q1. You read the first input. What's the first input? 0. Do you understand that? Adini Fuja and Lawrence. Okay. All right. Lawrence, do you understand that? That this is the first symbol of the string. Okay, so let's continue. So once you read the first symbol of the string, you are here now. Here, you're at Q1, right? That's the first symbol. That's the start point. So you have read the first input. So you see, where is 0 leading you to on this diagram? This is the input 0. Look at the arrow. It's keeping you where? At Q1. Do you understand that logic? Jenny Fuja and Lawrence, do you understand that logic? Okay. Yeah, I'm not seeing any response from the two of you again. Or have you been thrown out? Lawrence and Nadine Fuja, do you understand? If you don't understand, let me know quickly. Okay. So Jane Fuja responded. Okay. No. Okay. So when you read the first input, which is 0, it keeps you on this point. Now, what is the next? Okay, just respond quickly. What's the next input that we have on this string? Any Lawrence or yeah, what's the next input? 1. Good. So you see, when you read a 1, once you read 0, it kept you on where? Q1. So when you read 1, it moves you where? Here to Q2. Right? So you have dealt with this input. What's the next input when you have read 1? That of course you read 1, it took you to Q2. What's the next input? 0. Good. So once you read a 0 on Q2, where does it take you to? This is Q2. You read a 0. Where does it take you to? Any of the two of you? No, it doesn't take you to 0 now. This is Q2. Good. It takes you to Q3. Lawrence, do you understand that? Okay, that means you get it. So it takes you here. When you read 0, it takes you to Q3. So let me clean again so that we continue. It takes you to Q3. So you are now at Q3 and you have read 0. The next one you read is what? 1. When you read a 1, now this is telling you that you can either read 0 or 1. So if you have a 0 to read, it will take you to Q2. If you have a 1, it will take you to Q2. So here, what you have to read is what? The next one to read is what? What's the next thing we are reading? Lawrence? 1. So if you read a 1, this is 1. It takes us where? To Q2, right? So the next thing we read is what? Is 0. Once you read the 0, where's the arrow leading to? Once you read the 1, it takes you to Q2. Now, on Q2, you read a 0. Where does it take you to? Good. It takes you to Q3. So you can see you start looping until you get to this last one. So when you read a 1, it takes you here. You read a 1, it takes you here. You read a 0, it takes you back. You read a 1, it takes you here. You read a 0, it takes you here, up until this last one. So this last one, let me clean so that you will see what. So you see this last one here. Once you have done all the reading, once you are here now on Q3, which is this second to the last 0, you read it, it brings you here. So the last one will take you to where? This point, Q3, Q2. So once it takes you to Q2, all these input string has been tested or have been read. So let's not say it has been read. So in as much as the last input took you to Q2, and Q2 having this double circle means that it is the accept state, right? It means that this string is accepted. Do you get it now? I'm not seeing your response. So okay, Ajeni Fuja. I think who is the next? Lawrence. Oh, great. So I think we can move on now. Okay, so moving on. So say, although state diagrams are easier to grasp intuitively, we need a formal definition too, for two specific reasons. So we could just be assuming that, okay, if you read this, it is accepted. If you read that, it is accepted. But we need a formal definition to clear all ambiguity that may arise. For instance, in the case of that doormat, that opens when there's somebody in front, there's somebody at the back. We need to define which of the states is the initial state. Should the door be open to be at the initial state, or the door should be closed to be at the initial state? So a formal definition clears all those ambiguities so that you just don't assume that, okay, I can decide to choose any of the states to be my initial state, right? So first, it resolves any uncertainty about what is allowed in a finite automaton. So if you were uncertain about whether finite automaton were allowed to have 0 accept states, or whether they have exactly one transition exiting every state, for each possible input symbol, you should consult the formal definition and verify that the answer is yes in both cases. Now, look at this fellow here, this diagram. You see here, for any other diagram, you see that for 0, for here, you have 0, just have one transition. Here, one transition, one input, then a transition, one input, one transition, one input, one transition. But when you go to this point, you have one transition, but 2 possible inputs. So this would have been well defined on the formal definition, so that we will not be in any form of confusion when we are reading our input symbol. So the second reason why we need a formal definition is that a formal definition provides notation. So good notation helps you think and express your thoughts very clearly. So it solves the issue of ambiguity, and it also helps in the expression of our thoughts. So the language of a formal definition is somewhat arcane, right? That means it's a form of secret or mysterious. It has having some similarities to the language of legal documents, right? So, I explained to you when we're in class that most of the judges, in pronouncing their judgments, use some elements of logic. So both need to be precise, and every details must be spelled out. So a finite automaton has several parts. It has a set of states. So here, what is the set of states here now? Q1, Q2, Q3. Those are the set of states. So how many states do we have here? Response. How many set of states do we have here? I need your response quickly. You guys are going to sleep again. How many set of states do we have here? Good. 3. All right, thank you. So we have 3 set of states. Moving on. So it has a set of states, and it has rules for going from one state to another, depending on the input symbol. So it has different rules for going from one state to another. So depending on the input symbol. So for this diagram, what is the input symbol here? The input symbols are what? 0s and 1. Is there any other input symbol that is different from 0s and 1? No. So the input symbol for this is what? 0s and 1. Now, it has an input alphabet that indicates the allowed input symbol. Oh, have I been kicked out again? No. Can you hear me? Hello, can you hear me? Okay. Okay, thank you. So we can continue. So it has an input alphabet that indicates the allowed input symbol. So we have some set of input symbols that can be allowed per time. Or the set of, like for instance, you could have A or B as against 0s and 1s that we have on the previous example. You could have I and J, depending on the input symbol that you want to look at. Then it has a start state. Of course, I'm sure you're aware of that, where the arrow points from nowhere to a uh, particular state, right? It is called the start state or the initial state, and a set of accept states. So you could have two or more input, or one or more input accept states. So it's not just that you have just one accept state, you have different accept states, right? So the formal definition says that the finite, okay, the formal definition says that a finite automaton is a list of those 5 objects: set of states, 1, input alphabets, 2, rules for moving, 3, the start states, which is the initial state, and the accept state, which is the final state. So how many we have? 5. Set of states, 1, input alphabets, 2, rules for moving, 3, start state, 4, accept state, 5. So in mathematical language, a list of 5 elements is often called a 5 tuple. So tuple means as much as. So it means as much as 5. Hence, we define the finite automaton as a 5 tuple consisting of 5 parts. So what are these 5 parts? We have looked at it. We have looked at them. So we use something called the transition function. Now, please, I think you should pay attention here so that you understand the basics. No, we have started entering into the seemingly well, it's not hard, but of course we have started entering into the topic gradually, where you have to start taking notes and making mental notes of a lot of issues and a lot of information that will be of use to you. So we use something called a transition function. Now, what's a transition function? Let me do an annotation. So you are at a state here, you are at another state. Let's say this state is A, right? And this state is B. Now, this arrow moving from this point is called the transition. So let's assume that the transition takes in an input of 1. This is the transition input. Excuse me. So what is now the transition function? The transition function is represented by delta, right? Is represented by delta to define the rules for moving. So the rules for moving is defined by this transition function. So once you're at A, you receive an input of 1, you move to B. It is this delta that defines how the rules for moving is achieved. So if the finite automaton has an arrow from state X, so let's look at the states. This is state X, right? If a finite automaton has an arrow from state, so we have 2 states, state Y. So this is an arrow moving from state X to state Y, labeled with the input symbol 1. So the input symbol is 1. That means that if the automaton is in state X, when it reads a 1, then it moves to state Y. Let's look at it. If the automaton is at state X, it reads an input of 1. This is the input. It moves to state Y. So when you are at X, you read an input 1, then you move to Y. Do you get this analogy? You are state X, you read a 1, you move to Y. Do you understand this? Let's have response quickly. Do you understand what I've done so far? Okay, thank you. Yes, yes, yes. Okay. So thank you for following. Oh, Lawrence, that's good. Anima Shaun, Abiade Fija, you too. That's good to know. So that means you are following now. So let me clear. So we can now indicate the same thing with transition function by saying that defining that transition function delta. So delta is the transition function is defined as once you are at x, you read an input of 1, then your next state is at state y. So the notation is a kind of mathematical shorthand. Putting it all together, we arrive at a formal definition of finite state automata. So we understand that this is a transition function, right? We have the initial states being pointed at by an arrow. We have a final state represented by a double arrow. We have the input symbol, which of this language of this string symbol 0 and 1. So when we put all of them together, what do we have? We have, going to the next page, sorry. So we have this. You have a finite state automata is a 5 tuple, which is made up of all these elements. You have Q is the finite set of states. What does it mean? That means you have numbers of states depending on the counts. Now, how many circles can you see here? How many circles can you see? 5. Good. So for these 5 circles, that means Q equals to what? 5, because you have 5 states. Do you understand that? Q equals 5. Do you understand why I say Q equals 5? Response, do you understand? Okay. So moving forward. So that means the number of states that you can count is the number of Q. So that means, let's assume that this is Q1, Q2, Q3, Q4, Q5. So what it means is that Q, okay, let me clean again. So you have Q1, Q2, Q3. So clear all this. So that means that Q1 to Q5 can be found in Q. That means that Q, or maybe any of these, maybe Q1 is an element of the states. Do you understand that? That means Q1 can be found in Q. Also, Q2 can be found in Q, because Q is equals to what? Q1, Q2, Q3, Q4, Q5. They are the set of states that are found in Q. Do you get that analogy? Yes, the number of states, yes. Okay, thank you. So moving on. Then we have this epsilon is a finite set of alphabets. That means when we say alphabets are symbols that are found in any string. So when you look at this 1, 0, 1, 0, the finite set of alphabets found here is what? Just 1, 0. Because the string is made up of 1, 0, right? So when you look at delta, I'm sure you know we were explaining what delta was the other time, a transition function. which is Q, upon the receipt of any of these alphabets, which is the input, you move to another state Q. So when you are at state Q, you receive an alphabet, it takes you to Q. So this Q can be what? Q1, and this other Q can be what? Q3. You understand that? So you could move from one state of Q, which I've said that Q1 is an element of, Q1 is an element of Q, Q2 is an element of Q, Q3 is an element of Q. So any of this big Q can be either Q1, Q2, Q3, and this Q can also be any of the states that are defined. So Q0 is an element of Q. That means Q0 here, instead of me starting at Q1, it is starting at Q0. It is part of Q. So it is found in Q, is the initial state. And we said that the initial state is pointed to by an arrow. Then F, or QF, is the final state of Q, or is a finite. When you say finite, that means it has a beginning and it has an end. So it's a finite state of Q, is the set of accept states, right? So QF, or F, is the accept state, which has what? A double arrow. Are we still following? Do we still understand? Do we still understand what we have done so far? Okay, Emmanuel raised his hand. Ajayi Emmanuel, so you can unmute and speak.
Okay, sir. Good afternoon, sir. So does this mean that it's possible for us to have more than one accept state?
Yeah, can you speak up a bit? It appears I can't hear you clearly.
Okay, sir. Can you hear me now?
Yes, please.
Okay, so my question was, does this mean that we can have more than one accept state?
Yes, you can have more than one accept states.
Okay. Okay, sir.
Yeah,
Thank
but
you,
for a starter, we want to start with you on just one accept state. As a matter of fact, we should not have introduced what is called accept state to you now, because it's a form of printing out, like modeling a system that is able to print out. But for the purpose of explanation, we want to state that you could have several accept states. As a matter of fact, you could have multiple input states, initial states, sorry. All right, so moving on. Now, you see this guy again has appeared here. The same MI that we were looking at earlier. So to define it formally, we have this. So our Q, now this is what I was explaining earlier. Our Q is all the states, Q1, Q2, Q3. Look at it. Q1, Q1, Q2, Q3. So they are all the states in Q. So Q1, Q2, and Q3. So those are the states which are seen as what? Q. So any of this Q can represent any of these. So the symbol in the string, or the alphabet in the string, are just what? 0 or 1. Then the movement, the transition function, is what? In this form. So when you look at Q1, you receive a 0. Look at, let me quickly explain this. Now you are at Q1, you get an input of what? 0. You move to what? Q1. Now you are at Q1, you receive an input of 1. you move to Q2. So you are done with Q1. Now you're at Q2, you receive a 0, you move to Q3. You're at Q2, you receive a 1, you move to Q2. You're at Q3, you receive a 0, you move to Q2. You're at Q3, you receive a 1, you move to Q2. So when you look at this analogy and you look at our M1, go and test it and you see that all this transition function is correct. Okay. Then the machine accepts anything. It's not really solving. No, it doesn't accept anything. Because I was seeing F in a subset of or equals to Q. Now, yes, once we are seeing F, it's ought to have been written as QF. But not all now, it depends. You could have that your states are not just Q. Your states can be A, B, C, D, right? So once you want to say this is the final state, all you say is that here, just put a double circle. So you can see this is different from Q. So it's just for the purpose of definition. When you see F, it means QF, Q final. The initial state can be Q naught or Q1, depending on your own style. For me, I prefer to use Q naught, but some people want to use Q1 at the starting state. Okay, will be something raised up this hand. Let me see. Yes, you can ask your question. You can remove
Okay,
your
sir.
headphones.
Okay, sir, can you hear me, sir?
Yes, please.
Okay, sir. I don't know who asked that. Is it possible for all the states to be accept states? So that was what I said. That that's why I typed that stuff and said then it's not really solving anything. If all the states are accept states, if it's in
Exactly.
Q1,
You
it's
can have all the
accepted.
states to be accept states.
Yeah. Thank you, sir.
All right. So moving on. So you cannot, you of course you understand how we came about this delta. Then you know what Q1 is for this guy. You see the Q1 is what? The initial state is Q1 as against our definition where we had our Q1 to be what? Q naught. So depending on what you want to use as your initial state, all we want to see is that we are seeing one arrow pointing at it, or you have defined it to be your Q naught, or the initial, depending on what you want to do, right? So, and of course, the final state, you have F, which is equals to, now you can see F here. It has been formally defined as Q2. Now look at the ones with double circle. It is the final state, Q2. So let's assume that we now say, okay, all the states, that is the end state must be F. Then what happens to Q2 here? So you define what you are saying as the final state, which here has been stated that it is what? Q2. In essence, if A is a set of all strings that M accepts, we say that A is a language of the machine M. So we say L in bracket open M equals A. In essence, if A is a set of all strings M accepts. So once you drive in any set of string, you see we try to test what? 1, 1, 0, 1 initially. Then later we tried 1, 0, 1, 0, 1, 0, 1, 0, 1. Right? So those are types of input string that automaton M1 can do what? Can accept. So if it can accept all those kind of strings, then it means that M recognizes A, or M accepts A. So we say that A is the language of the machine M. So if you can understand Hausa, maybe I just change to Hausa now, and you can understand, that means Hausa is your language because you are able to accept that language as something you can relate with, right? If I switch to Igbo and you understand Igbo, that means that is the language you can recognize, and that is the language you can accept, right? So if you can understand all the three languages, Yoruba, Igbo, Hausa, and English, four, that means those languages are within the scope of the language or the languages you can recognize. However, when we go further, we will see, though you can understand some of those languages, you may not be able to interpret those languages effectively. For instance, as I'm speaking now, there's a possibility for those of you who grew up in the village, like those of you who are Easterners that go to your village for Christmas, there's a possibility that you will interpret what I'm saying to your native language before turning it to English. You may be doing it unconsciously and you will not know. So the language you can understand or you can recognize is a language you can accept. So because the term accept has different meanings, we will refer to machine accepting string and machine accepting languages. We prefer the term recognize for language in order to avoid confusion. So a machine may accept several strings, right? Just as we have tested for M1, but it always recognizes only one language. So language is a form of shorthand, right, to the summary of all the languages that can be understood by that automaton. So if a machine accepts no string, at least it can still accept an empty language represented by lambda. So in our example, let's say that A is defined as this, that's W, given that W contains at least one, that's one, that's one binary number 1, and an even number of 0, followed the last by last 1. So what we are saying is that in this language definition of A, we have the first input must be 1, then the next set of input string must be an even number of what? Zeros. What is an even number? We start with 2. So we can have 1, 0, 0, then followed by the last 1. So the kind of language or string that can be sent through this automaton is what? 1, 0, 0, 1. That's the list. So anything that is different from this formation may not be accepted. So if you have 1, 1, 0, 0, 1, because you have 1, 1, so the language say contains at least 1, 1. So that means it can still contain some other ones behind it, and even numbers of zeros. So if you have 3 zeros, that means that's violated the rules. So then the language that M1 can recognize is A, or equivalently, M1 recognizes A. That's what it means, as it were. So I can see some of you already shouting that you're tired of the class because it's 2, right? So me too, I'm already tired of teaching tired students. So we jig ourselves with test 1, and this is our test 1. So can you get this out? Can you quickly draw this? Now show that this figure above accepts string A, B, AA, BB, and that all those ones, then define the figure above formally. So that's your assignment, not test now. So please get this out in your notes, solve it, and you send it to your class rep. When you solve it in your Foolscap, you scan it, you send it the soft copy, PDF copy to your class rep. So your class rep will send it to me latest by tomorrow, 12 noon. Latest by tomorrow, 12 noon. Class rep, did you hear that? Okay. Yes, you can speak.
Yes, sir, I heard.
I can't hear you.
I said I heard. I heard you,
Oh,
sir.
okay. Your voice is quite far, or you are using earpiece or something.
Sir.
So you submit by 12 tomorrow. Okay, Aturashi. Okay, that's the second class rep. All right. Yeah. Do you have another class now? Class rep? Or do we assume that we'll finish this one? Okay.
No, sir.
I can't hear you.
No, sir, we don't.
Oh, okay. Let me just come. We just have a few pages, just 3 pages more. So we'll be done.
Okay, sir.
All right. So moving on. So that's your assignments. All right. So formal definition of computation. So far as we have described finite automata informally using state diagram and with formal definition as a 5-tuple, the informal description is easier to grasp at first, but the formal definition is useful for making the notation precise, resolving any ambiguity that may have occurred in the informal description. Next, we do the same for the finite automaton computation. We already have an informal idea of what it computes, and we now formalize it mathematically. So let M should be Mi, being a 5-tuple with Q, epsilon, delta, Q naught, and F, be a finite automaton, and let W, which is defined from Wi or 1 to n, be a string, right, where each Wi is a member of the alphabet epsilon. Then M accepts W if a sequence of states R0, R1 to Rn is in Q. So you can see, instead of using Q1, Q2, we have defined it as R1, R0, R1, R to Rn should be in Q. So these are the states now being defined as part of the state, exist within 3 conditions. The first one is that R0 is equals to Q0, which is what? The initial state. Then it has a transition function stating that when you are at Ri and you receive any of the inputs in W, which is the next from 0, it moves to a state R1 plus 1 for I equals 0. That means the starting point of I equals 0, and to n minus 1. And 3, Rn, which is the final or the final finite state, is an element or is the final state. So condition 1 says that the machine starts in the start state. Condition 2 states that the machine goes from state to state according to the transition function. Condition 3 states that the machine accepts its input if it ends up in an accept state. So we say that M recognizes language A if A is from the symbols of W. So a language is called a regular language if some finite automaton recognizes it. Thank you for listening to this class, and I hope that you can go over the recorded version of it. I think, let me see if I can copy YouTube address. Oh, you guys are happy. Better don't run away. Oh. I'm still going to take another attendance now. Coming. Copy stream link. So please check the chat and find where you look at the streaming link, and you may wish to subscribe if you wish. So that's the streaming link that I was using.